So, very good evening everyone. Just confirm audio video is clear. Please confirm audio video is clear. Just confirm audio video is clear. Please confirm audio video is clear to everyone. Audio video is clear. Just check and confirm. Audio video is clear, just confirm. So, a very good evening everyone. I welcome you all to the YouTube platform of IMS Gate Academy. Myself Prateek Mishra, and we are conducting the Smart Revision series to revise the subject in just a very short span. Today we will going to see one of the very important subject, which is the basics for civil engineering students and also for mechanical engineering students. My dear students, we are talking about none other than the subject of strength of materials. One of the very easy subject. Some tricky questions are framed from this subject, but from these sessions, I'll make sure that you have all the basics which are required to solve the questions. So just stay tuned till the end of the session and I'll make sure you to revise the entire content. So this is the session for strength of material. Before that, I have to make certain announcement. The first announcement is related to our Telegram group. If you want to get job regular updates, job notification updates, you can join our Telegram group, and even to enjoy the daily technical quizzes, you can join our Telegram group. The link is given in the description box. Regarding our YouTube series, all the schedules and the PDF of the lectures you will get in the Telegram group. So you can join that. Next is, we at IMS Gate Academy, dear students, we offer you with 4 different types of courses. Online program, offline program, hybrid program, and the self-learning program, where we provide around 800 hours of live teaching with interaction. We give you theory and exercise book. Especially in our exercise book, the questions are well placed in level 1, level 2 and level 3, so that even you can analyze what is your preparation level. We provide you with gate question bank, which contain 30+ years of gate questions with alternate solutions, with video solutions, with key points, with chapter overview. We provide you with 12 personalized one-to-one mentoring sessions, where a student discussed about all the personal strategies to improve his efficiency for day-to-day reading. We provide you with the test series, where we provide with 130+ tests, including chapter test, subject test, multiple subject test, advanced subject test, and the full-length mock test with the video solutions. So these are our course detail at our IMS Gate Academy. So with these words, let's start the very interesting subject of strength of material. So strength of material, first of all, my dear students, for civil engineering students has a weightage of around 4 to 6 marks. This is for civil engineering students. For civil engineering students, it has a weightage of 4 to 6 marks. For mechanical engineering students, it has a weightage of 6 to 8 marks. For mechanical engineering students, right? Now, especially if I talk about strength of material, there are so many varieties of application-based question that can be framed from this subject. Good evening, Thiru sir. Good evening. So let's start one by one. So the first chapter of strength of material is known as simple stresses and strain. The first chapter of strength of material is simple stress and strains. Simple stress and strains. Okay. Now, whenever we are dealing with any topic of strength of material, our body will be always under static equilibrium. Static equilibrium means the body will not be moving. the forces, the external load that will be acting over the body will be balanced external loads, right? That's why whenever we will be taking any body like this, over this body there will be balanced external load acting like this. So this is the external load that is acting like this. Now this external load is trying to deform this body, and this body will undergo elongation like this. This body will undergo elongation like this. So the amount of deformation this body is undergoing is delta L, right? This body will going to resist this deformation, and in order to resist this deformation, there will be the development of internal resisting forces inside the body. In order to resist this deformation caused by the external load, there will be the development of internal resisting forces. Now the first term is stress. Stress is defined as the internal resisting force developed per unit area. Stress is defined as internal resisting force, internal resisting force developed per unit area. Internal resisting force developed per unit area. So if you consider the FBD of only this much portion of the body, if I consider this much portion of the body, this is the external load P. And in order to resist the deformation caused by this external load P, there will be the development of internal resisting forces R. There will be the development of internal resisting forces R. Now I said that this body is under the state of static equilibrium. It means that the summation of forces should be equal to 0. So from this I can write P is equal to R. Means the external load P is equal to the internal resisting force R. Now what happens is, while writing down this stress, instead of this internal resisting force, I write down this P. And now you know how we are writing this P. So this stress is equal to P by area. P by area. This is the stress. Stress is defined as the internal resisting force per unit area. Now, when this body will undergo deformation like this, the cross-sectional area of the body will also going to reduce. So if you want to visualize this, you can visualize it like this. This is my body. This is my body, over which an external load P is acting like this. And when this body will undergo deformation, the cross-sectional area of this body will going to reduce. This is the cross-sectional area. This is the reduction in the cross-sectional area, how it will going to happen. Earlier, the length or the original length of the body is L0. Now it has changed to L. The cross-sectional area which was A0, now it changed to A, right? A and L are known as the instantaneous area and the instantaneous length. Now for writing down stress, which area I should choose? Whether I should choose the original area or whether I should choose the instantaneous area. Based on this, the stresses are classified into two categories. Based on this, which area you are choosing? The stress are of two types. So types of stresses. So the first type of stress is known as true stress or actual stress. True stress or actual stress. Now true stress or actual stress is defined as internal resisting force per unit actual area, that is your instantaneous area A. When you take this A, very good evening Ganesh. So when you take this instantaneous area A, that gives you the true or actual stress. If you are taking this original area A0, it is known as engineering stress. It is known as engineering stress or nominal stress. Engineering stress or nominal stress. Now this engineering stress or nominal stress epsilon naught is equal to resisting force divided by original area A0. Okay. For all our calculations, we go with this engineering stress or nominal stress, but this is also the definition, or this is also one of the type of stress. Okay. So this is the thing about stress. Now you can see here, due to this external load, the body is undergoing deformation and there is the change in length that you are observing. This change in length that the body is undergoing, is delta L. The change in length that the body is undergoing is delta L. Now I define one more thing that is known as strain. So strain is defined as change in length per unit length. Strain is defined as change in length per unit length. Okay. Change in length per unit length. So this is equal to delta L by length. Now again, which length you are taking, whether you are taking the original length or whether you are taking the instantaneous length, the strain is again defined as two types. So the first type of strain is known as actual strain or true strain. Actual strain or true strain. Actual strain or true strain. This is equal to, actual strain or true strain is equal to change in length per unit instantaneous length. That is this length L, right, which is shown in blue. So actual strain or true strain is equals to change in length per unit instantaneous length. The next type of strain is known as engineering strain or nominal strain. Engineering strain or nominal strain, and this is equal to epsilon naught, which is change in length per unit original length L naught. So this is the type of strains and stresses based on which area in which length you are taking. For all the calculation purpose, we go with this engineering stress and engineering strain. For all the calculation purpose, we go with this engineering stress and engineering strain. Now there is one relation between actual strain and the engineering strain, and that is relation between actual strain and engineering strain. Relation between actual strain and engineering strain. So your actual strain, epsilon actual, is equal to epsilon naught into natural log of L by L naught. Your actual strain is equals to epsilon naught. This is actual strain is equal to natural log of L by L naught. Natural log of L by L naught, right? So your d epsilon is equal to dl by L, change in length per unit length. When you integrate this, so this will be 0 to epsilon actual, and this will be from L naught to L. So this will be epsilon actual is equal to natural log of L by L naught. Okay. So this is another expression for your actual strain. It is not a relation between actual strain and engineering strain. This is just an expression for your actual strain. So this is another expression for your actual strain. So this is another expression for your actual strain. This is actual strain. Now next is relation between actual stress and engineering stress. Relation between actual stress and engineering stress. Relation between actual stress and engineering stress. So actual stress, relation between actual stress, epsilon sigma actual, and engineering stress, sigma naught. So actual stress, sigma actual, is equal to sigma naught into 1 plus minus epsilon naught, where sigma A is your actual stress, sigma naught is your original engineering stress, and epsilon naught is your engineering strain, right? So this is the thing. After this, you have the next thing, which is termed as Hooke's law. Now, first of all, Hooke's law is defined for all the isotropic, homogeneous and elastic material. So the assumption that we take in Hooke's law is material is homogeneous, isotropic and elastic. The assumption that we take in Hooke's law is material is homogeneous, isotropic and elastic. Material is homogeneous, isotropic and elastic. Now, if the body is subjected to axial load like this, if this is my body and it is subjected to axial load P, if the body is subjected to axial load P, there will be a development of axial stresses, and the axial stress developed is sigma. Then as per Hooke's law, your stress is directly proportional to strain. Stress is directly proportional to strain. So stress is sigma is directly proportional to epsilon. Removing the proportionality sign, sigma is equal to E into epsilon. So this is your Hooke's law for axial loading. Similarly, Hooke's law for shear loading is Hooke's law for shear loading. Hooke's law for shear loading is, so shear loading will give shear stress. Okay, I'll draw this. Shear loading will going to give shear stress. So if you have a body like this, and a shear load like this is applied, this is your shear load F. If you apply the shear force over this body like this, right? So this body will undergo deformation like this. This body will undergo deformation like this. This is the deformation that this body will going to undergo. This is the deformation that this body will going to undergo like this, right? So this is your shear force. This shear force divided by the resisting area. This is your shear force F divided by this top area will going to give you the shear stress. So tau shear stress is equal to shear stress tau is equal to shear force divided by the resisting area. Shear force divided by the resisting area. Now for this shear force, this top area will be my resisting area. So shear stress tau is equal to shear force F divided by this resisting area A. This is your resisting area A, right? This is your resisting area A. So shear stress is shear force divided by the resisting area. Now this is your shear strain phi. This is your shear strain phi. This shear strain phi is always measured in terms of angle. If this is some height h of the element, and this body is getting deformed by some delta x, right? This is the deformation delta x and this is height h. Then shear strain phi is equal to shear strain phi is equal to delta x by h. Then shear strain phi is equal to delta x by h. This is your shear strain phi. Now Hooke's law is also defined for this shear loading. So Hooke's law for shear loading says that shear stress is directly proportional to shear strain. Shear stress is directly proportional to shear strain. Shear stress is directly proportional to shear strain. Means tau is directly proportional to phi. When you remove this proportionality sign, you have tau is equal to G into phi. Now this G is known as modulus of rigidity or shear modulus. G is known as modulus of rigidity G is known as modulus of rigidity or shear modulus. This is known as modulus of rigidity or shear modulus. All these are elastic constants. Here G is the elastic constant. In the previous case, you can see here, this Young's modulus E is the elastic constant, okay. So, two Hooke's law we have seen. First one is for your axial loading. Second one is for your shear loading. Now comes the third Hooke's law. Third Hooke's law is for hydrostatic loading. So, Hooke's law for hydrostatic loading. Hooke's law for hydrostatic loading. Hooke's law for hydrostatic loading, right? So, hydrostatic, as the name says, hydrostatic means if this is my body like this, if this is my body, hydrostatic means that in all the directions, the pressure that is acting over the body is same. So, the pressure that is acting in all the directions over the body, this pressure is same. The pressure which is acting in all the direction, it is same. So, change in pressure is delta P, change in pressure is delta P, change in pressure is delta P. When the body is moved from the surface to some height, there will be some change in pressure that will be acting. Now, due to this change in pressure, due to the pressure acting in the body in all the direction, this body will undergo compression and you will see the change in volume. So, Hooke's law is defined between this change in pressure and the volumetric strain. Change in volume is defined with respect to the volumetric strain. So, as per Hooke's law, your change in pressure is directly proportional to the volumetric strain. So, change in pressure is directly proportional to the volumetric strain. So, delta P, change in pressure, is directly proportional to the volumetric strain epsilon V. Removing the proportionality sign, you will get delta P is equal to K into epsilon V. Now, here K is known as the bulk modulus. Here K is known as the bulk modulus. Here K is termed as the bulk modulus. K is termed as the bulk modulus. Now, my dear student, again this K is the elastic constant, right? This K is again the elastic constant. So, we have seen three elastic constant. First one was the Young's modulus. Second one was the shear modulus. Third one was the bulk modulus. Now, coming to the fourth elastic constant, which is known as the Poisson's ratio. Which is known as the Poisson's ratio. Which is known as the Poisson's ratio mu. Which is known as the Poisson's ratio mu. Now, this Poisson's ratio mu tells us about the lateral change in length. Okay, you can see here, if this is my body like this is my body like this, right? And due to external load, this body will undergo elongation. Due to this external load, this body will undergo elongation. So, if for general, if I mark this length as L, this width is B and this height as H. So, due to this external load P, the length of the body will going to increase, but the other two dimension will going to contract. This contraction of the lateral dimension is explained using the Poisson's ratio. If you apply this external load P, the other two dimensions will going to contract. The other two dimensions will going to contract like this. The other two dimensions will going to contract like this, and you will get the body like this. You will have the body like this. You will have the body like this. You can clearly see that this height from H is reduced to H dash. this width from B is reduced to B dash, but the length is increased. Doesn't matter. If you apply the load, the length of the body will going to increase. So the direction in which the load is applied is termed as longitudinal direction. Direction of load is 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 longitudinal direction. The directions which are perpendicular to the load are termed as lateral direction or transverse direction. But now the directions perpendicular to the load, directions perpendicular to the load, directions perpendicular to load are termed as lateral directions. The directions perpendicular to the load are termed as lateral directions. So you can see here, when you apply this load, the length is increasing but the other two dimensions are reducing. That is explained using the Poisson's ratio. Now this, if you write the strain along the length or along the longitudinal direction, that is termed as your longitudinal strain. That is termed as your longitudinal strain. The strain written along the longitudinal direction is longitudinal strain, delta L by L. Right now my direction, you observe the direction of the load, okay? I'm not fixing anything. It is a very generalized term. You observe the direction of load. If the direction of load is along L, then L will be my longitudinal direction, okay? So if I'm analyzing the body in which the direction of load is along length, then the strain written along length will be my longitudinal strain. The strain written along the lateral directions will be my lateral strain. The strains which are written along the lateral direction will be my lateral strains. So this can be written as delta H by H or delta B by B. Two lateral directions I have, okay? And you can clearly see that the nature of these two strains will be opposite. If longitudinal strain is positive, the lateral strain will be negative. They will be contracting. On the other hand, if your longitudinal strain is contracting, then the other two strains will be expanding. So the nature of these two strains will be opposite. I write here the nature of strains will be opposite. 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 Now this Poisson's ratio tells me the ratio of lateral strain to longitudinal strain. Poisson's ratio mu is the ratio of lateral strain. It is the ratio of lateral strain to longitudinal strain. Lateral strain to longitudinal strain. Poisson's ratio mu is the ratio of lateral strain to longitudinal strain. Now we have to make this ratio positive. And one thing I have already told you, that the nature of lateral strain and longitudinal strain will be opposite. So I keep one minus sign in order to keep this entire ratio as positive. So Poisson's ratio mu is minus of lateral strain to longitudinal strain. Poisson's ratio mu is equal to minus of lateral strain to longitudinal strain. It is equal to minus of lateral strain to longitudinal strain. So I got my fourth elastic constant. My fourth elastic constant is mu. So I got four elastic constants: Young's modulus, shear modulus, strain curve for mild steel. Stress strain curve for mild steel. Next topic is stress strain curve for mild steel. Stress strain curve for mild steel. Stress strain curve for mild steel. Next is stress strain curve for mild steel. The next is stress strain curve for mild steel. I write start like this. This is my y-axis in which I am going to plot the stress, and this is my x-axis in which I am going to plot the strain. Here I will start with one very simple question: why the strain is plotted on the x-axis or the independent axis? Why the strain is plotted on this axis? My dear student, when you apply the load over the body, first a strain will come. The body will undergo deformation. In order to resist that deformation, the stresses are produced. Okay. So first strain will come. In order to resist the strain, stresses are produced. So strain is the independent quantity and stress is your dependent quantity. That's why strain is always plotted on the x-axis, that is your independent axis, and stress is always plotted on your y-axis, that is your dependent axis. So this is strain epsilon and this is your stress sigma. Which stress we are plotting, which strain we are plotting? We are plotting engineering strain, right? And engineering stress. All the things that we are discussing here are engineering stress and engineering strain. Now when you apply the load over the mild steel bar, initially the stress will be proportional to strain and you will get a straight line like this. Initially the stress will be proportional to strain, and at this point A, which is known as the proportionality limit, up to A, your Hooke's law is valid. Okay, up to A, your Hooke's law is valid, means stress is proportional to strain. What is the slope of this line termed as? Anyone? What is the slope of this line known as? The slope of this line is known as the Young's modulus. The slope of this line is termed as the Young's modulus, right? Beyond this, when you apply more load, now the stress will not be proportional to strain, but still the body will be under the elastic limit. So this is your linear portion. Beyond point A, when you apply the load, the body will be undergo non-linear deformation, and this B is known as your elastic limit. This A to B is your non-linear portion. This A to B is non-linear portion. This A to B is non-linear portion. Now beyond till point B, if you remove the load, the body will going to regain its original shape and size. There is no permanent deformation happened over the body till point B, and the strain up till point B is known as your elastic strain. The strain up till point B is known as your elastic strain. This is known as your elastic strain. This is epsilon elastic. This is your elastic strain. Beyond point B, if you apply any load, there will be the plastic deformations. Beyond point B, when you apply the load, you will get the upper yield point and then lower yield point. This is C dash, upper yield point, and this is C, the lower yield point, right? Whatever yield strength that you take of the body is corresponding to this lower yield point. The yield strength of the body is corresponding to this lower yield point. The yield strength of the body is corresponding to lower yield point. So yield strength sigma y is corresponding to lower yield point. Sigma y is yield strength. Sigma y is yield strength. Sigma y is your yield strength, right? Now, you can see here from A to B there is no non-linear portion. From B onwards there will be plastic deformation happening. Then you can see the loss of stress from C dash to C. There is sudden jump. Now this loss of stress is because of the slippage of carbon atoms which are present in the crystal structure of the steel. Due to slippage of carbon atom, you see this fall in stress value at the same strain. Now beyond this point C, if you without any addition of load, the body will show huge deformation and you will get yield plateau here. This CD is termed as yield plateau. This is yield plateau. Now during yielding, what is happening? Reorientation of the crystal structure is happening. Due to yielding, the reorientation of the crystal structure is happening. At this point D, now you have got the new configuration of the steel body. You have got the new configuration of the steel material, which is more strong than the previous material, which is more strong than the original material. If this material is more strong due to reorientation, it will going to offer more resistance against the external loads. So here you will get beyond point D, you will get the strain hardening zone. Here you will get the strain hardening zone. In this strain hardening zone from D to E, this is your strain hardening zone from D to E. So D to E is your strain hardening zone. This strain hardening zone offers more resistance against external loading. This is your strain hardening zone which offers more resistance against external loading, right? This D to E is your strain hardening zone which offers more resistance against external loading. Then you have this point E, which is known as the ultimate load point. And at this point E, beyond this, if more loading is provided, then the body will start undergoing necking. And that necking is the reduction in the cross-sectional area. Beyond point E, the body will start undergoing necking, and at this point F, you will see the failure of the body. So this EF is known as your necking zone. This EF is known as your necking zone. This is known as your necking zone. And F is known as your fracture point or failure point. If we are talking about the material, which is a ductile material, due to tensile load, it will undergo shear failure. It will undergo shear failure. That's why you observe the necking and you observe the failure plane at 45 degrees for ductile material. We will talk about that also, what are ductile material, what are brittle material. The strain corresponding to this F is known as the fracture strain. So we have defined one type of strain which is known as elastic strain. Beyond this point B, whatever strain will be coming over the body, that is known as your permanent strain or plastic strain. So this is known as, this strain is known as plastic strain. This is known as plastic strain or post-elastic strain. This is known as your plastic strain or post-elastic strain. Based on these values, we have defined one term that is known as ductility. Okay. So we have different properties of the material. One of the property is ductility. You know that ductility is the property of the material by virtue of which it can be drawn into thin wires. But that will not work in GATE exam. In the GATE exam, if you need to compare between two materials, that which one is more ductile, which one is less ductile, then some technical definition is required. Now, if I would like to give you the technical definition of ductility, the material is said to be ductile. Please remember my words. The material is said to be ductile if post-elastic strain or this plastic strain is more than 5%. What are ductile material? Ductile materials are those materials for which the plastic strain or the post-elastic strain is more than 5%. What are ductile materials? So ductile materials are those materials are those materials for which post-elastic strain, post-elastic means plastic only, post-elastic or plastic strain is more than 5%, or plastic strain is more than 5%. Plastic strain is more than 5%, is more than 5%, right? So this is how we define the ductility. So one common question, okay, which material is more ductile? So how you need to compare it? Using the post-elastic strain. Whichever material has more post-elastic strain will be more ductile in nature, as simple as that. So whichever material has more post-elastic strain, whichever material has more post-elastic strain, has more post-elastic or plastic strain, or plastic strain is more ductile, whichever material has more post-elastic strain or plastic strain is more ductile in nature. So this solves the question of the ductility comparison, right? Now again there is one more comparison, that which material is elastic. Now the student has this common confusion. They start imagining, okay, we can extend rubber very easily, very quickly, and we can extend rubber like this much amount. So rubber is said to be more elastic. No, first of all, rubber is not elastic. I tell you, if you need to compare between the elasticity of two materials, you compare their Young's modulus. If you need to compare the elasticity between two material, compare the Young's modulus. Compare the Young's modulus. Compare the Young's modulus. Compare the Young's modulus. Compare Young's modulus. Whichever material has more Young's modulus will be more elastic. Whichever material has more Young's modulus will be more elastic. More Young's modulus, more elasticity. 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 Whichever material is more elastic will going to have more Young's modulus, right? So this kind of comparative questions again you can expect in the examination. Sir, in this result come from the characteristic strength. No, my dear Shubham, characteristic strength is separate. That is totally separate. First of all, we don't talk about characteristic strength when we are talking about mild steel. We talk about characteristic strength when we talk about the concrete. Okay. So characteristic strength is separate. Here we have talked about one thing which is known as the yield strength. Yield strength we get from mild steel. That characteristic strength is characteristic strength is defined as, okay, this is for civil engineering student. Characteristic strength is defined as that strength below which not 5% of the samples are expected to fall. Okay. So that thing we will deal in RCC. Right now you stay in strength of material. We are talking about mild steel. For mild steel there is nothing like characteristic strength. There is something called as yield strength. For mild steel it is a ductile material and we talk about the yield strength. Okay, so this is how you need to compare between the ductility and the elasticity of the body. Okay, now there are different curves. There are different curves. So depending on the type of material, so stress strain curve for different materials. Stress strain curve for different materials. Curve for different materials. Stress strain curve for different materials. Stress strain curve for different materials. Okay. So usually in the examination, one curve is drawn to you and you are asked which material is this. Okay. So let me draw one by one all the curves. So first I'll draw like this. This is my first curve. This is the stress strain plot, right? For stress strain plot, I got this. This is the curve which is drawn for stress strain. This is the curve that is drawn for stress strain. And now they are asking which type of material is this. So what you have to do, how to solve this? This you have to solve just by using your mind, observing, okay, this portion is the elastic portion and this portion is the plastic portion. And you can see this line is horizontal, right? So this is your elastoplastic material, where whichever material which have both elastic and the plastic zone is defined as elastoplastic material. This is elastoplastic material. This is elastoplastic material. This is elastoplastic material. This is elastoplastic material. Like this you have to observe. You have to observe whether elastic portion is there, plastic portion is there, or which portion is there, right? So right now you can see this is your elastic portion, this is your plastic portion. It is signifying yielding. So this is your elastoplastic material. Similarly, I can draw the another curve like this. I can draw the another curve like this. This is my another curve. So if I draw a curve like this, if I only draw a curve like this, quickly tell me which material is this? It is showing which property? The only property that is visible in this curve. Please tell me. Which type of material is this? Quickly. Chalo, quickly. This material is showing which property? Only one property this material is showing. It is showing elastic property or plastic property. This material is showing elastic or plastic property. Quickly tell me. This material is showing elastic or plastic property. This material is showing only and only elastic property. Very good, very good. This material is showing only elastic property. That's why it is defined as elastic material. This is my only elastic material. This is my elastic material. This is my elastic material, right? Now comes the third curve. Please quickly. This comes the third curve. When you have this third curve, for this third curve, this is the stress strain plot. This is the stress strain plot. This property, this material is showing which property? This material is showing which property? Elastic or plastic? This material is showing which property? Elastic or plastic? Quickly. This material is showing which property? Very good, Shubham. Very good, Ganesh. This material is showing which property? Elastic or plastic? Quickly. Quickly, quickly. Your answers are weighted. Which property is shown by this material? Elastic or plastic? Elastic or plastic? Quickly. This material is showing which property? Elastic or plastic? Very good. That's why this is classified as ideal plastic material. This is known as ideal plastic material. This is known as ideal plastic material. Okay. If I draw one stress strain curve like this, if I draw one stress strain curve like this, if I draw one stress strain curve like this, if I draw a stress strain curve like this, right? If I draw one stress strain curve like this, so this is the stress strain curve. This is the stress strain curve like this, okay? This is the stress strain curve I have drawn. This is the stress strain curve I have drawn. Observe this very carefully. This is the stress strain curve I have drawn. This is my stress strain curve. Now the thing is, very good, Krishna. This is the stress strain curve. You can see here, whatever load you are applying, the body is not undergoing any deformation. The body is not undergoing any deformation. No matter whatever load you have applied, no matter whatever stress is there on the body is not undergoing any deformation. The body which doesn't undergo any deformation are termed as rigid bodies. The bodies which don't undergo any deformation are termed as rigid body. So this is a rigid material. This is a rigid material. This is a rigid material. This is a rigid material which don't undergo any deformation no matter whatever load you apply. Now comes the next material. This is my next material. The next material is like this. Now this you have to identify. This is a trick question for you. This is a trick question for you. I am telling you. This is a trick question for you. You have a body like this. This is the body. This is the body, right? This is the body. Now you can see here, this body has both elastic region also and plastic region also. But in the plastic region, the stress is not constant. Means the stress is increasing. It means that they are talking about the strain hardening zone. So this is the elastoplastic material with strain hardening. As you can see here, there is an increase in stress. So this is your elastoplastic material. This is your elastoplastic material. This is your elastoplastic material with strain hardening. This is your elastoplastic material with strain hardening. With strain hardening. This is your elastoplastic material with strain hardening. This is your elastoplastic material with strain hardening, because this plastic zone is not horizontal. If this would have been horizontal, I would have only read elastoplastic material. But since it is showing some sign of strain hardening, so we say that this is elastoplastic material with strain hardening. Now comes my next material. Next material is very simple. Next material is very simple. Next material is very simple. This is my stress strain curve. Next material is very simple, and I expect all the answers from you. I expect all the answers from you. If the stress strain curve for the material is like this, if the stress strain curve for the material is like this, right? If the stress strain curve for the material is like this, it means that even under the action of a slightest load, the body is showing huge deformation. So such is the material. Such material are fluid materials. The fluid materials are those materials under the action of slightest shear force. They undergo huge deformation. So this is an example of ideal fluid. 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 So all these materials, any one material can be asked in your examination. Please keep a check, right? Now, even in general, if any material is given to you, so what you have to identify, whether any elastic region is there or not, whether any plastic region is there or not. If there is a plastic region, whether it is a straight region or it is an increasing region. If it is an increasing region, then it is strain hardening. If it is a straight region, we simply say it is a plastic material. Okay, so all these different types of material can be asked in a multiple select question. Chalo, after this, moving on, the next topic of discussion is elongation of the bars. The next topic of discussion is elongation of bars or elongation of prismatic bars. Elongation of prismatic bars. Elongation of prismatic bars. The next topic of discussion is elongation of prismatic bar. First of all, what are prismatic bars? Prismatic bars are those bars for which the cross-sectional area is constant throughout the length. Prismatic bars will be those bars for which the area of cross-section is constant throughout the length. So if this is my prismatic bar, which is over which a load of P is acting, this is my prismatic bar over which a load of P is acting like this. A load of P is acting like this, right? The length of the bar is L. The area of cross section of the bar is A, and Young's modulus of the bar is E. The length of the bar is L, area of cross section is A, and the Young's modulus of the bar is P. Then by Hooke's law, what I say? Hooke's law says that stress is equal to E into strain. Stress is equal to E into strain. Sir, is there any significance of low yield point? Beta, the lower yield point is highly significant. Corresponding to lower yield point, we report the yield strength. Upper yield point is not that much significant because as soon as the material reaches the upper yield point, that takes the slippage of carbon atoms, and again from C dash to C, the stress value falls. So whatever yield strength we take for the material is corresponding to the lower yield point. Okay. Chalo, moving on with this. So I was talking about the elongation of the bar. For calculating the elongation, again I am going to apply the Hooke's law. As per Hooke's law, stress is equal to E into strain. Stress is equal to P by A. Stress is equal to P by A is equal to E into change in length per unit length. All the stress and strains are the engineering stress and strains, right? Now you can rearrange this to calculate the deformation of this bar or the elongation of this bar. So when you rearrange this, you will find that delta L is equal to P into L upon AE. Delta L is equal to P into L upon AE. This is the deformation or the elongation of the bar, delta L. Now here I would like to tell you one very, very important point. This AE is termed as the axial rigidity. AE is termed as the axial rigidity. This is termed as axial rigidity. This is termed as axial rigidity. What does axial rigidity tells us? Axial rigidity tells us how strong is the material against axial deformation. If axial rigidity of the material is more, means more is the strength of the material against axial deformation. So if I have to compare two materials and I have to compare which material will going to offer more resistance against axial deformation, then you have to compare their axial rigidity. For example, if I give you two materials like this is my material A, this is my material B, right? This is my material A, say this is my material 1, this is my material 2. For this, area is A1, Young's modulus is E1, area is A2, Young's modulus is E2. And I ask you which material will offer more resistance against axial deformation. I ask you which material offers more resistance against axial deformation. So without applying any brain, you will say, sir, we will going to compare the axial rigidity. Whichever material will have more axial rigidity will going to offer more resistance against deformation. So whichever material has more axial rigidity, whichever material has more axial rigidity will offer more resistance or will be more strong or will offer more resistance against axial deformations, right? Or will be more strong in axial deformations. So you need to compare the axial rigidity. Don't worry about this PDF that I am writing, you will get in the Telegram group. So just listen. what I am saying. Already you have prepared the notes. Keep on revising with me, right? All these points are very important. You may get a multiple select question from this area. Two materials are given. Which material is more strong? Whichever material has more value of axial rigidity will be more strong. So axial rigidity is AE. AE, so you need to compare whichever material has more value of axial rigidity. For that, you have more resistance against axial deformation. Now there is one more term which is known as axial stiffness. So AE by L is termed as axial stiffness. Is termed as axial stiffness. This is also termed as axial stiffness. This is termed as axial stiffness, right? Now axial stiffness is the more accurate parameter. Axial stiffness tells us about the resistance offered by the material per unit length. So if you need to compare between axial rigidity and axial stiffness is the more accurate parameter to tell you or to convey, to explain about the strength of material against axial deformation. Okay. So axial stiffness is AE by L, which again tells us the resistance offered by the material per unit length against the axial deformation. Okay. So this is how you calculate the elongation of the material of the prismatic bar. Now comes the non-prismatic bar. So next is elongation of non-prismatic bars. Elongation of non-prismatic bars. Non-prismatic bars. Elongation of non-prismatic bars. So in elongation of non-prismatic bar, first one is the series connection. First one is the series connection. When the non-prismatic bars are connected in series. Series connection. When the non-prismatic bars are connected in series. So when you see this, these are my non-prismatic bar. This is my first bar. Then this is my second bar. Then this is my third bar. Okay. Material can be different. Cross-sectional area can be different. Length can be different. I am keeping the most general case. This is my material 1, this is my material 2, this is my material 3. Different materials. Area of cross section is A1, Young's modulus is E1, length of this bar is L1. Area is A2, Young's modulus is E2 and length is L2. Area is A3, length is L3 and Young's modulus is E3. Now this non-prismatic bar is subjected under the external load of P. It is subjected to the external load of P, right? Now you can see here, sir, hi, आज मेरा first class है. Very good, Shubham, very good. Shushma, sorry, very good. So when you have this non-prismatic bar and it is acted over the external load, then when you draw the free body diagram, you will observe that all the components are under the action of same load P. If you draw the free body diagram of this first bar, if you draw the free body diagram of this first bar, it is under the action of load P. It is under the action of load P. This is first bar. If you draw the second bar, it will be also under the action of load P. The second bar is also under the action of load P. If the second bar is also the under action of load P, if you draw the free body of the third bar, the third bar is also under the action of load P. This third bar is also under the action of load P, right? So if the bars are non-prismatic and they are connected in series, then all the bars will be under the action of same load. So all the bars will be under the action of same load. All the members of the bar, are under the action of same load P. Are under the action of same load P. All the bars will be under the action of same load P. Now, when all these components of the bar are under the action of same load P, all these components will individually undergo elongation. this first material will undergo elongation of delta L1, this second material will undergo elongation of delta L2, and this third material will undergo elongation of delta L3. So if you want to calculate the total elongation of bar, the total elongation of bar is delta L1 plus delta L2 plus delta L3. So whenever bars are connected in series, the total elongation of the bar will be different, and the sum of the elongation of the individual component will going to give you the total elongation of the bar. So the total elongation of the bar, 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 delta L is the sum of the individual component, sum of the elongation of individual component. So delta L is equal to delta L1 plus delta L2 plus delta L3. Total elongation delta is the sum of the individual component delta L1, delta L2 and delta L3. Now just write down all the threes. So delta L is equal to delta L1 plus delta L2 plus delta L3. Now this delta L1 is equal to P into L1 upon A1 into E1. This is the elongation of the first bar. First bar is under the action of load P. So the elongation of this first bar is P into L1 upon A1 into E1. Similarly, elongation of the second bar is equal to P into L2 upon A2 into E2. So this is equal to P into L2 upon A2 into E2. Similarly, the elongation of the third bar is equal to P into L3 upon A3 into E3. This is the total elongation of the bar. So whenever the bars are connected in series, non-prismatic bars, right, and they are under the action of only and only one load, then the load and all the components will be same. The total elongation is the sum of the individual elongations, right? Now next is when the bars are connected in parallel. I'll just write down this properly. So this is equal to delta L is equal to P L1 upon A1 E1 plus P L2 upon A2 E2 plus P L3 upon A3 E3. This is the total elongation of the bar of the non-prismatic bar when the components are connected in series. Second one, when the components are connected in parallel. So parallel connection, parallel connection, right? When the components are connected in parallel, observe this. So you have this first component, you have this first material component. This is your first material component. And then this is your second material component. Now whenever the parallel connection will be made, one thing is ensured that length of both the materials is same. Length of both the bars is same. The area of cross section can be different and Young's modulus can be different. Means your axial rigidity can be different. Area is different, Young's modulus is different, means axial rigidity for both the material is different. Now when you will apply this load P over this assembly, when you apply this load P over this assembly, both the materials will undergo same deformation delta. So whenever the materials are connected in parallel or whenever the bars are connected in parallel, they will undergo same deformation delta. So for parallel connection, deformation will be same. Deformation will be same. Both the materials will undergo same deformation. Both the materials will undergo same deformation. Both the materials will undergo same deformation, that is delta. Both the material will undergo same deformation delta, right? Both the materials will undergo same deformation delta. Now clearly observe this. The material is having different axial rigidity, means they have different strength against the axial deformation. So if they are undergoing same deformation delta, then the amount of load causing that deformation will be different, right? This load P is distributed in the form of P1 and P2 to cross the deformation delta in these two bars. This load P is distributed in the form of P1 and P2. The upper material will have load P1 and the lower material will have load P2 in order to undergo same deformation delta. Now this load P is equal to P1 plus P2. What is P1? P1 is the load taken by material 1 to undergo deformation delta. What is P2? P2 is the load taken by material 2 to undergo deformation delta. Now there is huge deformation, means huge complicated calculation for that. I tell you one simple word. What is P1 and P2? P1 and P2 are nothing but the weighted average of their axial rigidity with respect to the total load. In simple words, you can write down P. Even without calculation, you can write down P1. P1 is equals to total load P multiplied by A1 E1. We are talking about first material. So P1 is equals to total load P into A1 E1 divided by the total axial rigidity A1 E1 plus A2 E2 directly. A2 E2. If you have to write down P2, so P2 is total load P. We are talking about second material, so A2 E2. A2 E2 divided by A1 E1 plus A2 E2 plus A2 E2. This is known as the weighted average of the total load with respect to the axial rigidity. So right now we have written the formula when two materials are connected in parallel. If there are n number of materials connected in parallel, you can write down the formula and be confident on that on solving the question, right? So usually in the question they will ask you how much amount of load is taken by material 1, how much amount of load is taken by material 2, like that. So for two materials, this formula is clear. For two material, this formula is clear. We will going to write down formula for three materials. If three materials are connected in parallel like this, if three materials are connected in parallel like this, if three materials are connected in parallel like this, if three materials are connected in parallel like this, say these are the three materials which are connected in parallel. This is my material 1, this is my material 1, then this is my material 2, this is my material 2, and then this is my material 3. If this is my material 3, all the materials will going to have the same length. Please keep a check on that. All the materials will going to have the same length L. All the materials will going to have the same length L, right? All the materials. So the material are taking different load. Yes, my dear, the materials will take different load. Earlier the load was same. In series connection, the load taken by all the components was same. Deformations are different. In parallel connection, deformation will be same, but loads will be different. Okay. So if this is my material 1, this is my material 2, this is my material 3, area of this material is A1 E1, area of material 2 is A2 E2, area of second material is A2 E2, and area of third material is A3 E3. Then this total load P that you have applied over this assembly, this total load P that you have applied over this assembly will be distributed as P1, P2 and P3. Will be distributed as P1, P2 and P3. Now the total deformation that all the materials will undergo is same. Then how they can have same deformation? Beta, axial rigidity is different, right? Axial rigidity is different. Axial rigidity is different. That's why because of the different load they have same deformation. Since their axial rigidity is different, that's why because of the different load they are undergoing same deformation. Okay, I am going to write that formula also. So if you want to write down the deformation delta, so this deformation delta is equal to P1 L upon A1 E1, P1 L upon A1 E1, and same deformation delta is equal to P2 L upon A2 E2. Now I think you can relate very well. P1 and P2 are different. A1 E1 and A2 E2 are also different. So the ratio A1 E1 by P1 is equal to A2 E2 by P2. That ratio is constant. That ratio delta is constant, right? Okay. So for these three material, under the action of this total load P, all the material will undergo same deformation. All the three materials will undergo same deformation delta. All the three materials will undergo same deformation delta, right? The total load P is equal to P1 plus P2 plus P3. The total load P is equal to P1 plus P2 plus P3. The total load P is equal to P1 plus P2 plus P3. Now, if you want to write down P1 directly, P1 is the weighted average of load P with respect to their axial rigidity. So, P1 is equals to P into A1E1 upon A1E1 plus A2E2 plus A3E3 plus A3E3 plus A3E3 plus A3E3. So this is your P1 load, right? Similarly, you can write down P2. So P2 is equal to total load into A2E2 divided by A1E1 plus A2E2 plus A3E3 plus A3E3. This is your total load. This is your load P2. Now you can write down P3. P3 is again the weighted average. P3 is equal to total load P into A3E3 divided by A1E1 plus A2E2 plus A3E3 plus A3E3. Now you have got the trick. Not just three material. If even n number of materials are given to you, you have to just observe. If you are writing P1, here P into A1E1 will be there, and in the denominator it will be the sum of axial rigidity of all the materials. For P2, it will be P into A2E2 divided by the sum of axial rigidity of all the material. Then third one, P3, A3E3 will be there. In the denominator, it will be the sum of axial rigidity of all the material, right? Generalized approach for writing down the loads. This deformation delta, if you want to write down this deformation delta, see here. If you want to write down this deformation delta, see here how I am writing this. So deformation delta is same for all the materials. Deformation delta is same for all the materials. Okay, I keep it here. Deformation delta is same for all the materials. So delta is equal to P1L upon A1E1. This is also equal to P2L upon A2E2. This is also equal to P3L upon A3E3. L will going to cancel out, and you can calculate the value of P1, P2, P3, whichever thing is required. Try to, whenever you get a question right in the examination, already the things are so tensed, go with the easy approach. Whichever thing is easy will stay in your mind for longer duration, okay? So this is your elongation of the bars, prismatic, non-prismatic bars, when the bars are connected in series, when the bars are connected in parallel. Now talking about the tapered bars. Elongation of tapered bars. Elongation of tapered bars. Elongation of tapered bars. So first one is having circular cross section. First one is having circular cross section. So circular cross section tapered bar. So this is a circular cross section tapered bar like this, where the diameter from one end is increasing from D1 to D2. The diameter is increasing from D1 to D2. Here the diameter is D1 and here the diameter is D2. The length of the bar is L and it is under the action of load P. the length of the bar is L, and it is under the action of load P. It is under the action of load P. So you have this circular tapered bar which is under the action of load P. The length of the bar is L and the diameter is increasing from D1 to D2. The Young's modulus of the material is E. So elongation of this bar, the total elongation of this bar, delta L, is equal to 4PL upon pi E D1 D2. Simple. What is the elongation of this tapered bar? The elongation of this tapered bar is 4PL upon pi E D1 D2, where P is the external load, L is the length of the bar, pi is pi only, E is your Young's modulus, D1 and D2 are your diameter of both the ends. So this is your elongation of the bar. Elongation of the tapered bar when the cross section is circular and it is increasing from D1 to D2. So change in length, elongation of the bar, delta L, is equal to 4PL upon pi E D1 D2. Please note this down. Okay, so this is your elongation. Now coming to the rectangular tapered bar. Rectangular tapered bar. Next is your rectangular tapered bar. Second is rectangular tapered bar. So this is your rectangular tapered bar. How should I draw this? Okay. So this is your rectangular tapered bar. Now for this rectangular tapered bar, the thickness is constant, right? This thickness is constant. This thickness of the bar is constant. This is T. But the depth, this depth or width of the bar is increasing from B1 to B2. This depth is increasing from, width is increasing from B1 to B2. It is under the load, external load P. It is under the action of external load P. This is load P. The width of the bar is increasing from B1 to B2. The length of the bar is L and Young's modulus is E. So elongation of this bar, delta is equal to elongation of this bar. Elongation of this bar is equal to delta is PL upon ET into natural log of B2 by B1 upon B2 minus B1. This is the elongation of this tapered bar, right? So elongation of this rectangular tapered bar whose width is B, and the thickness is constant T. The elongation is equal to PL upon ET natural log of B2 by B1 upon B2 minus B1. So this is the elongation of this bar, right? This formula is very important. Because sometimes you can expect a direct question from here, right? You can expect a direct question from here. Just wait for 2 seconds. I'll be back. The next one is elongation under self-weight. Elongation under self-weight. Just stay calm, stay relaxed, and I'll make sure that you revise the entire subject of strength of material. Whatever things is possible today, we will going to see it today, and whatever things will be left, we will going to see it tomorrow, right? So next one is elongation of the bar under self-weight. So this is the bar which is hanging from the roof. The length of this bar is L. Area of cross section of this bar is A. The length of this bar is L. Area of cross section is A. Young's modulus is E. And the unit weight of the bar is gamma. Gamma is the unit weight of the bar. Then elongation under self-weight. Elongation under self-weight. So first I write down gamma is the unit weight. Gamma is the unit weight. Then elongation under self-weight. Elongation of the bar. Elongation under self-weight. Elongation under self-weight. This is equal to gamma L square divided by 2E. This is the elongation of the bar under self-weight. Okay. You can clearly see in this elongation, nowhere there is a mention of area of cross section. So the elongation under self-weight does not depend on the cross-sectional area. This elongation under self-weight does not depends on the cross-sectional area. Does not depends on the cross-sectional area. But this elongation is directly proportional to the square of the length, right? So this elongation is directly proportional to L square. So please keep a check on these two things. Sometimes what they do is they will change the length, they will change the cross-sectional area, and they will ask what is the ratio of the elongation under self-weight in first condition with respect to the second condition. Okay. So there you can go with these things. Okay. So this is the elongation of the bar under self-weight. Now comes the very, very important topic. Please give the next heading, stress tensor. Stress tensor. Stress tensor. Next is stress tensor. Stress tensor. As you already know, stress is a tensor quantity. Now what is a tensor quantity? Tensor quantity are those quantities which have magnitude and have two directions. So stress is a tensor quantity, and tensor quantities are those quantities which have two directions. So if I write down sigma xx, then this is the direction of plane. This is the direction of plane. This is the direction of plane over which this stress is acting. And this second x is the direction of load. This second x is the direction of load due to which this stress is coming. This second x is the direction of load due to which this stress is coming. Similarly, if I write down tau xy, here tau xy, this x means the direction of plane. This x means the direction of plane. Direction of plane. And direction of plane is always represented in the form of the unit vector. Okay, whatever is the normal vector perpendicular to that plane explains the direction of the plane. And this y is the direction of load. This y is the direction of load. This y is the direction of load. Now we see the stress tensor. Okay. So if I draw one object in front of you, if I take one element like this, if I take one element like this, this is my 3D element. This is my 3D element, okay? And the three directions are, this is my x direction. I have mark here. This is my x direction. This is x direction. This is y direction. This is y direction. And this one is my z direction. Okay. So this plane will be my x plane, this plane will be my y plane, and the plane which is in front will be my z plane. So if I am drawing a stress like this, which is perpendicular to the plane, this stress is named as sigma x, since it is acting on the x plane. and it is produced due to the load along x direction. That's why I write this as sigma xx. So sigma xx is the stress acting on the x plane due to the load along x direction. Similarly, this is a stress which is acting on the y plane. This is the stress which is acting on the y plane due to the load along y direction, right? The third one is this. This is my third stress. This is my third stress. This stress is acting along z direction. This stress is acting along z direction. This stress is acting along z direction due to the load along z direction. So this is known as sigma zz, right? Similarly, this is the shear stress which is acting on the x plane. This is your shear stress which is acting on the x plane due to the load along y direction. Similarly, if I talk about this shear stress is acting on the y plane due to the load along x direction. This stress will be produced when the load is acting along x direction. That's why it is named as tau yx, right? Then you have this shear stress. This shear stress is acting on the x plane due to the load acting along z direction. So this is tau xz. Then you have this shear stress. This shear stress is acting on z plane due to load along x direction. So this is known as tau zx. This is tau zx. Then this is the shear stress which is acting on z plane due to the load along y direction. So this is tau zy. Then this is the shear stress which is acting on y plane due to the load along z direction. So this is tau yz. Okay, so I think I have mentioned all the stresses and strain, all the stresses, right? Now this stress is represented in a form of matrix which is known as stress tensor. So stress tensor is sigma xx, then you have tau xy, then you have tau xz, then you have tau yx, then you have sigma yy, and then you have sigma yz. Then you have last tau zx, then you have tau zy, and then you have sigma zz. So this is the matrix which is termed as the stress tensor. From this stress tensor, we can calculate strain tensor. So for strain tensor, for writing down strain tensor, what you need to do is, wherever sigma xx is there, you need to replace it with epsilon xx. And wherever tau xy is there, you need to replace this with phi xy by 2. Just remember these two things and you can write down strain tensor from the stress tensor. So from stress tensor, the strain tensor can be written as, here you have sigma xx, so I will write down epsilon xx. Here you have tau xy, so I will write down phi xy by 2. Then here I have tau xz, so I will write down phi xz by 2. Okay. Then here I have tau yx, so I will write down phi yx by 2. Then here I have sigma yy, so I will write down epsilon yy. Here I have phi, this is tau yz. Why I have written sigma yz? This is tau yz. This is tau yz. This is tau yz. So this will be phi yz by 2. Then this one is tau zx, so this will be phi zx by 2. This will be phi zy by 2. This will be phi zy by 2, and this will be your epsilon zz. Okay. Now when you observe both these metrics are symmetric metrics. Both the 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 metrics are symmetric metrics. Now if I say that this is my symmetric matrix, so I can write down tau xy is equal to tau yx, tau xz is equal to tau zx, and I can write down tau yz is equal to tau zy. Okay. So if this is my symmetric matrix, then these are the things. Your non-diagonal elements should be equal. For this strain tensor, you can write down phi xy is equal to, or phi xy is equal to phi yx, phi xz is equal to phi zx, phi yz is equal to phi zy. So this is your symmetric elements, right? So this is how you write down the stress tensor and the strain tensor. Chalo. So once you know the value of stress tensor and strain tensor, next thing is to write down the strains for different complicated loadings. So first, if you have the uniaxial loading, so for uniaxial loading, in which the element is only subjected to sigma x, when the body is only subjected to sigma xx, then your strain along x direction, epsilon xx, this is equal to sigma xx by E, right? Epsilon xx is equals to sigma xx by E. Now, when you see this element, due to this sigma xx, the length of the element will going to increase, but the lateral dimensions will going to contract, means the dimensions along y and z will going to contract. So epsilon z, epsilon yy, this is equal to minus mu times of sigma xx by E. This is termed as the Poisson's effect. This is your longitudinal strain, this is your lateral strain. So lateral strain is equals to minus mu times of your longitudinal strain. Similarly, you can write down epsilon zz. This is equal to minus mu times of sigma xx by E. So when you have the uniaxial loading, this is how the strains will vary. Okay. Second, for biaxial loading like this, if you have an element like this, which is subjected to biaxial loading, this is sigma x and this is sigma y. This is sigma x and y. If the element is subjected to biaxial loading like this, sigma y, right? In order to write down the strain along x direction, now remember, there will be the elongation due to the sigma x, but there will be the contraction of the length due to the Poisson's effect of sigma y, right? So what you write down, epsilon x is equal to sigma x by E. This will elongate the member, but this sigma y, epsilon x is equal to sigma x by E, that will going to elongate the member, but the sigma y will going to contract the member along x. So minus the Poisson's effect of sigma y. So minus mu times of sigma y by E. So this is your strain along x direction. Similarly, strain along y direction. So along y direction, the sigma y will going to increase the length. So this is equal to sigma y by E. Then due to this sigma x, there will be the contraction along y. So minus Poisson's effect of sigma x by E. So this is how you write down the strain along x and y direction. Okay. Now next is strain along z direction. So along z direction, both sigma x and sigma y will going to contract the length. So epsilon z, this is equal to minus mu times of sigma x by E minus mu times of sigma y by E. means along Z there will be the Poisson's effect of sigma x and sigma y. So directly you can write down the strain along x, y and z direction. You have to only consider the value of strain due to direct load and the Poisson's effect due to the load in the other load in the other axis. So this is for biaxial loading. Now coming to triaxial loading. For triaxial loading, when the load is acting in all the three directions, sigma x, sigma y, sigma z, all things are present. When you have the loading in the triaxial, if you have triaxial loading, so this is sigma x, this is sigma x, then you have sigma y, you have sigma y like this is sigma y, and then you have sigma z, this is sigma z, right? Now here the Poisson's effect of other two stresses will come, okay? So whenever you are having the triaxial loading, if you have to write down a strain along x direction, so strain along x, epsilon x is equal to sigma x by E. This will going to increase the length, but other two stresses will going to contract the length along x direction. So minus Poisson's effect of sigma y by E minus Poisson's effect of sigma z by E directly without any confusion. Sigma x will going to increase the length along x direction, but sigma y and sigma z will going to reduce it. Similarly, if I have to write down strain along y direction, this is equal to sigma y by E minus the Poisson's effect of sigma x, so minus mu times of sigma x by E minus the Poisson's effect of sigma z, minus mu times of sigma z by E, okay? Now writing down the strain along z direction, this is equal to sigma z by E minus the Poisson's effect of sigma x, so minus mu into sigma x by E minus mu into sigma y by E. So this is how you can write down the strain along x, y and z direction. Now my dear students, once you got the strain along x, y and z direction, you can write down the total volumetric strain. So volumetric strain, epsilon V, volumetric strain epsilon V is equal to epsilon x plus epsilon y plus epsilon z. Volumetric strain is equal to epsilon x plus epsilon y plus epsilon z. You can substitute all the three values to get the volumetric strain. Or if I write down directly, volumetric strain epsilon V is equal to sigma x plus sigma y plus sigma z into 1 minus 2 mu divided by E, This is your volumetric strain, right? So volumetric strain epsilon V is equals to sigma x plus sigma y plus sigma z into 1 minus 2 mu divided by E. Now volumetric strain tells us about the change in volume. If the change in volume is 0, then what we can figure out is either your sigma x plus sigma y plus sigma z is equal to 0, the sum of the stresses. If the sum of the stresses sigma x, sigma y and sigma z is equal to 0, then the volumetric strain will be 0, or mu is equals to 0.5. So I'll write like this: for volumetric strain to be 0 means change in volume is 0, delta V is 0, means change in volume is 0. Then we say that either sum of sigma x plus sigma y plus sigma z is equal to 0. So if the sum of the stresses sigma x, sigma y, sigma z is equal to 0, then in that case you will get volumetric strain equal to 0. And also 1 minus 2 mu equal to 0. So from here the value of mu is 0.5. So directly If the value of mu is given to you as 0.5, then you say that the change in volume will be 0. And the material in which the change in volume is 0 is termed as incompressible material or rigid material, which can be only defined if the value of mu is 0.5. So for any material, if the value of mu is 0.5, then we say that it is a rigid material or an incompressible material. So if the value of mu is 0.5, then we say that the material is incompressible. Material is incompressible. Material is incompressible. We say that the material is incompressible or rigid only when the value of mu is 0.5. Now here I would like to mention one point. Mu is the property of the material. Mu is the property of the material. That's why we are commenting on the nature of the material, whether the material is incompressible or not. Here we are not commenting on the nature of material. This is for any general material. For any general material, if sum of the stresses is equal to 0, then the volumetric strain has to be 0. But if the material is incompressible, it means the value of Poisson's ratio has to be 0.5. I can again prove you in one more way. You know that your change in pressure is equal to volumetric strain divided by bulk modulus, right? For incompressible material, bulk modulus is infinite. For incompressible material, bulk modulus tends to infinity. For incompressible material, the bulk modulus tends towards infinity. Means that whatever load you apply, whatever pressure you increase, there will be no change in the volume. So if bulk modulus tends to infinity, I can write down E is equals to 3K into 1 minus 2 mu. E is equals to 3K into 1 minus 2 mu. Take this side. So E by 3K is equal to 1 minus 2 mu, right? So again, if K tends towards infinity, then this ratio will be 0, and again you will get the value of mu as 0.5. So two proofs for you that if the material is given as incompressible, you can directly take the value of mu as 0.5. Or the second interpretation that you can do is, if the value of mu is given as 0.5, you can imagine that it is an incompressible material. Okay. So this is about your stress tensor. Now moving ahead, next topic of discussion is thermal stresses. The 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 kind of effort I am putting it, just one small request from you, please share this session, whichever friend is there for you. Thermal stresses. Now thermal stresses is because of the restraints, the hindrance that you create in the free expansion of the material due to change in temperature. Now, sir, you have said such a long statement, I am not getting anything. Now, one thing I'll tell you. If this is my object, if this is my material like this, lying peacefully over the surface, sir, last week में mock test लगाना है या केवल revision करना है? तरंग दोनों चीज करना है, मॉक टेस्ट के साथ में रिवीजन करना है. एंड बेस्ट थिंग आई टेल यू, राइट सर, लास्ट वीक में या आप मॉक टेस्ट इसलिए मत लगाइए क्योंकि आपको मार्क्स चेक करना है. मॉक टेस्ट इज फॉर द इंप्रूवमेंट. गेट द फीडबैक. किन सब्जेक्ट्स में आपको प्रॉब्लम है, किन सब्जेक्ट्स में आप फॉर्मूला रिकॉल नहीं कर पा रहे हो, फॉर ऑल दोज थिंग्स मॉक टेस्ट आर देयर. स्टूडेंट क्या करता है कि मॉक टेस्ट दिया, मार्क्स चेक किया और साइड कर दिया, और जैसे ही आपने मार्क्स चेक करके मॉक टेस्ट को साइड किया, आपने अपना टाइम वेस्ट कर दिया. आप मॉक टेस्ट दीजिए, 3 घंटे का मॉक टेस्ट पूरा अटेम्प्ट करिए सिंसियरली, उसके बाद उसमें 2 घंटे दीजिए ये देखने के लिए कि कहां कहां आपने मिस्टेक किया है, किन सब्जेक्ट्स में आप फॉर्मूला रिकॉल नहीं कर पा रहे हो, किन सब्जेक्ट्स में आप कॉन्सेप्ट अप्लाई नहीं कर पा रहे हो. उसके लिए मॉक टेस्ट होना चाहिए. एक रेंज रखिए कि आप टेस्ट से पहले, गेट एग्जाम से पहले, ये जो मेरा लास्ट 2 हफ्ता बचा हुआ है, इसमें मैं एटलीस्ट 5 से 6 मॉक टेस्ट दूंगा. मींस मैं हर ऑल्टरनेट डे एक मॉक टेस्ट दूंगा. और अगर मैं हर ऑल्टरनेट डे एक मॉक टेस्ट दे रहा हूं, तो मैं अपने मार्क्स को, अगर राइट नाउ मेरे मार्क्स 30 आ रहे हैं, तो मैं उनको धीरे धीरे इंप्रूव करूंगा. आप क्या करते हो, आप टेस्ट नंबर 1 में आपके मार्क्स आए कितने, टेस्ट नंबर 1 में आपके मार्क्स आए 20, आप हो गए डिमोरलाइज, राइट। आपने क्या किया, टेस्ट को बंद किया और ये सोचने लग गए कि मैं कहां से रिवाइज करूं। बच्चा, अगर आपके 20 मार्क्स आ रहे हैं तो आप ये चेक करो कि आपने किन सब्जेक्ट्स के क्वेश्चन छोड़े हैं, किन सब्जेक्ट्स में आपने क्वेश्चन अटेम्प्ट ही नहीं किए हैं, किन सब्जेक्ट्स में आपने सिली मिस्टेक्स करी हैं। उस एनालिसिस को लिखो। गिव 2 hours of your time after the test. The total test in your mind should be like 5 hours. 3 hours for the test and 2 hours for the analysis. That analysis is very important. रिवीजन तो होता रहेगा, रिवीजन के साथ रिवीजन किस चीज का करना ये भी तो पता चले। वो पता करने के लिए एनालिसिस जरूरी है। फॉर एग्जाम्पल, आपके पास 8 सब्जेक्ट हैं, आपने टेस्ट दिया, उसमें से पता चला कि 4 सब्जेक्ट ऐसे हैं जहां पे मेरा कंसेप्ट एप्लीकेशन वीक है, तो मैं क्या करूंगा, इन 4 सब्जेक्ट्स के लिए अगेन अपनी थ्योरी बुक को रिवाइज करूंगा। जो भी मेरे पास नोट्स है, रिवाइज दैट फॉर रिमेनिंग 2 सब्जेक्ट्स। और मेरे को ऐसा लगा कि 2 सब्जेक्ट में मेरा फॉर्मूला रिकॉलिंग नहीं हो पा रहा है, तो इन 2 सब्जेक्ट्स के लिए मैं क्या करूंगा, मैं डेली फॉर्मूला शीट रिवाइज करूंगा इन 2 सब्जेक्ट्स के लिए। और ये मैं कहां से आइडेंटिफाई कर पाया हूं, आफ्टर एनालाइजिंग द टेस्ट। सो एनालिसिस इज वेरी इंपॉर्टेंट। सर, एनआईटीज के लिए कितने मार्क्स लाने पड़ते हैं? अगर आपका कुछ भी स्कोर 40+ है तो आप एनआईटी, मैं अच्छी ब्रांचों की बारे में बात कर रहा हूं, मैं कॉम्प्रोमाइज सिचुएशन के बारे में बात नहीं कर रहा। अगर आपको अच्छा कुछ चाहिए एनआईटी के अंदर, आपको एटलीस्ट 40+ मार्क्स सिक्योर करना पड़ेंगे, एंड दिस इज फॉर सिविल इंजीनियरिंग स्टूडेंट्स। इफ यू बिलोंग टू मैकेनिकल इंजीनियरिंग स्टूडेंट, यू हैव टू सिक्योर एनीथिंग अबव 45 मार्क्स, anything above 45 marks, and at least target good selection from IITs and NITs. ऐसे को तो आप कोई भी ब्रांच ले लो, आपको 35 मार्क्स में भी ब्रांच मिल जाएगी एनआईटी में, लेकिन दैट इज ऑफ नो यूज। इफ यू आर टारगेटिंग एनआईटीज, टारगेट एनीथिंग अबव 40 मार्क्स। फॉर सिविल इंजीनियर्स एंड फॉर मैकेनिकल इंजीनियर्स, एनीथिंग अबव 45 मार्क्स विल बी इंपॉर्टेंट। चलो, so we were talking about thermal stress. What are thermal stresses, right? So इसको बहुत अच्छे से समझना। thermal stress क्या होता है? thermal stress में क्या होता है बच्चों? First of all, when you increase the temperature of this body will going to expand freely, right? There will be no development of any kind of stress. The length of the body is L. If you increase the temperature of this body, the length of the body will going to increase. This increase in length delta L, this increase in length delta L is equal to L alpha delta T. This increase in length is equal to L alpha delta T. Sir, if in CSE branch, for CSE branch again same thing yaar, CSE branch to is like booming. You don't have any possible option for CSE branch. First of all, for all the IITs and NITs, you have one branch called Computer Science and Engineering, right? You have only one single branch for Computer Science and Engineering. Then you have some substitute branch like Artificial Intelligence, Machine Learning. Then you have Data Science, Data Analytics. All those things we have introduced this year. So you can take up anything, especially for NITs also. Anything above 40 marks. Anything above 40 marks is good, irrespective of any branch. Okay, so I was talking about this thermal stress. So due to the increase in temperature over this body, the length of the member will going to increase. If I talk about the other dimensions, the other dimensions will also increase, but there will be no development of any stress inside the body, because the body is kept freely on the surface. This is my body, it is kept freely on the surface, right? This is a block which is kept freely on the surface. If you increase the temperature, if the temperature of this object is increased, then what will happen? This length, width and height, this length, width and height of the material will going to increase. And you will see that the dimension of the body is now this. This is the dimension of the body now. This is the dimension of the body. I think you can clearly identify the new dimension. This is the dimension. The length is increased to L dash, the width is increased to B dash, and the height is increased to H dash. Okay. Due to increase in temperature, all the 3 dimensions will going to increase, and there will be no development of stress because you haven't restricted this body anywhere. So the free expansion along length, So change in length or free expansion along length. Free expansion can be written as free expansion delta L is equal to L alpha delta T. Free expansion along width delta B is equal to B alpha delta T. And free expansion along height is equal to H alpha delta T. This is the free expansion along length, width and height. Okay. Now when the body is undergoing free expansion or free contraction, there won't be development of any thermal stress. Under free expansion and free contraction, please remember this. Under free expansion and free contraction, under free expansion or contraction, so if you are increasing the temperature, the body will undergo expansion. If you reduce the temperature, the body will undergo contraction. So under free expansion and contraction, the body will not experience any stress. Under free expansion or contraction, the body will not experience any stress. Okay. So if I give you a body and I increase the temperature of the body and ask you, what is the thermal stress developed? You will say, sir, it is not restricted. Since it is undergoing free expansion, so there will be no development of thermal stresses, right? Now, for the same body, if I restrict it, if I restrict this body, right? If I keep this body in between the support, and this support is not allowing the free expansion along the length. And if I increase the temperature of the body now, since it is restricted along x direction, so there will be the development of thermal stresses along x direction like this. There will be the development of thermal stresses along x direction like this, right? There will be the development of thermal stresses. If I increase the temperature of this body and this body is restricted along x direction, so there will be the development of thermal stresses like this. There will be the development of thermal stresses like this. So first of all, thermal stress is the property of the material. Please observe this. Thermal stress is the property of the material. Is the property of the material. Is the property of the material. Okay. Thermal stress is the property of the material. Now since this body is restricted along length, the total elongation along length is equal to 0. The total elongation along length is 0. Total change in length is 0. Now this change in length is, first of all, due to increase in temperature, there will be free expansion. There will be free expansion that will try to increase the length of the member. But this increase in length of the member is restricted by this thermal stress. So this free expansion is nullified by the effect of thermal stress minus effect of sigma thermal stress, and this should be equal to 0. So what is free expansion? Free expansion is L alpha delta T. This is your free expansion. Now effect of sigma is sigma by E, and this should be equal to 0. Don't remember the formula. I am again telling you, don't remember the formula, remember this. Remember how we are forming this equation. So change in length along the length is equal to 0. This change is equals to the free expansion minus effect of sigma. So free expansion is L alpha delta T and effect of sigma is sigma by E, and this should be equal to 0, right? So this is your equation. From here you can calculate the value of thermal stress sigma, but this is not the ultimate expression for calculating the thermal stress. Usually what happens is, a student remembers this. Every time they get the thermal stress, they directly apply this, and that is the actually wrong practice. Okay, you have to see in how many directions the restrictions are provided, in how many directions the restrictions are creating the thermal stress. So right now you are restricting it along the x direction. So when you are restricting it only along one direction, the free expansion along the length is not possible, and that is how you create the value. Now there will be expansion along the other two dimension since there is no restriction. So expansion along width, expansion along width, expansion along width, expansion along width B. This is equal to, so delta B is equal to free expansion B alpha delta T. This is the free expansion, right? Plus, since this sigma is compressive, it will try to increase the length of, it will try to increase the other two dimensions. The other two dimensions are width. So plus effect of sigma. So effect of sigma is sigma by E. This is your strain multiplied by B. So this is your expansion along width. Expansion along width is free expansion along width plus effect of sigma, which is sigma by E multiplied by B, right? Similarly, expansion along depth or height, expansion along height, expansion along height, expansion along height, H. So this expansion along height delta H is equal to free expansion, which is H alpha delta T, plus effect of thermal stress. So effect of thermal stress is plus sigma by E into H. Sigma by E into H. So this is how you can calculate the free expansion along the width and free expansion along height by equating the total expansion along width, total expansion along length equal to 0. Okay, so these formulas are important. Instead of formulae, if you can just remember how these things are written, it will be more helpful. So this is when you are restricting the member along one direction. So this is when you are restricting the member along one direction. So this is first restriction along x. Second is restriction along y. The second is restriction along x and y. Restriction along x and y means along the length and along the height, the material cannot expand freely, right? Along the length and along the height, the material cannot expand freely. So this is your material and it is restricted along x and also along y. It is restricted along x and also along y like this. It is restricted along x and also along y like this. So this is how you have restricted the material. This is how you have restricted, right? Now when you increase the temperature, okay, along the length, due to this restriction, there will be the development of thermal stresses because this support will not allow the free expansion of the material, and this support, due to this support, there will be the restraining force offered against the free expansion of the material. So due to this support along x direction, there will be the development of thermal stress along x direction. There will be the development of thermal stress along x direction, and I name this as sigma x. there will be the development of thermal stress along x direction, and I name this as sigma x. Now, due to the restriction along y direction, there will be the development of thermal stress along y direction. There will be the development of thermal stress along y direction like this. There will be the development of thermal stress along y direction like this, and this is your sigma y. There will be the development of thermal stress along y direction, which is equal to sigma y. Now, I have already told you that thermal stress is the property of the material, and my material is homogeneous and isotropic, means the property of the material is same in all the points in all the direction. The property of the material is same at all the points in all the directions, means sigma y is equal to sigma x is equal to sigma. The value of thermal stress, will be same because this is the property of the material. But why I have written sigma x and sigma y? Because I want to write down the equations. Okay, you remember this. Proper thermal stress will be same along x and y direction because thermal stress is the property of the material. Now, first thing, net expansion along x is 0. So delta net along x is 0. So when you write down delta net along x will be free expansion along x. Delta net is first free expansion along x. Then minus effect of this sigma x, because sigma x is reducing the length. So minus effect of sigma x. Now you see here, this sigma y is compressive, so it will try to increase the length. So plus effect of sigma y, plus effect of sigma y, and this should be equal to 0. In my mind, I know that sigma x is equals to sigma y is equals to sigma. But just to write down the equation correctly, I have taken sigma x and sigma y in order to give you the full clarity how I am writing down the equation. So free expansion is L alpha delta t. This is free expansion. Then effect of sigma x minus sigma by E into L. Okay, here also I have to write down L. I have missed L here. This is sigma by E into L. Please check, this is sigma by E into L. So here also this is sigma by E into L. This is the effect of sigma x. Then the Poisson's effect of sigma y. So plus mu times of sigma by E into L. And this should be equal to 0. So L alpha delta t minus sigma by E into L plus mu times of sigma by E into L. And this should be equal to 0. So this is my first equation. Second is delta net along y should be equal to 0. So along y you have the height, right? So it includes free expansion along y, This includes free expansion along y minus effect of sigma y, plus effect of sigma x, and this should be equal to 0, right? So this is my second equation. Now just write down free expansion along y is equal to h alpha delta t. This is h alpha delta t. This is free expansion along y minus effect of sigma y. So this is sigma by E into h. Then the Poisson's effect of sigma x. So plus mu times of sigma by E into h. And this should be equal to 0. So this is my next equation. So these two equations are important. Now if I have to write down free expansion along z, because this material is free to expand along z. So free or expansion along z. So expansion along z. So expansion along Z includes free expansion, which is B alpha delta T. This is free expansion along Z plus the effect of sigma x and sigma y. So plus mu times of sigma by E into B. This is effect of sigma x plus effect of sigma y, which is mu times of sigma by E into B. This is your expansion along Z. Okay. So you have to first understand in which direction the restraints are there, whether the temperature is increasing or decreasing, all those things. Once you have analyzed that, then only you can write down all these equations. Now next one is when the restraint is along all the three directions. When restriction is along x, y and z. Third, restriction is along x, y and z. Restriction is along x, y and z. X, y and z. When the restriction is along x, y and z, then the thermal stress will be produced along x, y and z direction, and all the three thermal stresses will be equal. So this is the body. Now this body is restricted in all the directions. So along x direction there will be the development of thermal stresses like this. There will be the development of thermal stress like this. This is sigma x. Then this is sigma x. Then there will be the development of thermal stress along y direction like this. This is sigma y. And then, this is sigma z. This is sigma z. And this is how the thermal stress will be produced along y direction. So this is your sigma y. Now this thermal stresses is the property of the material. That's why we say that sigma x is equal to sigma y is equal to sigma z is equal to sigma. Thermal stress is the property of the material. That's why sigma x will be equal to sigma y will be equal to sigma z. Now if you have restricted along all the three directions, then in any direction the free expansion is not possible. Means delta net along x, y and z direction should be equal to 0. So one by one I will write delta net along x is equal to 0. So this is equal to free expansion. This is equal to free expansion minus effect of sigma x. Then sigma y and sigma z will try to increase the length. So plus effect of sigma y and sigma z. Plus effect of sigma y and sigma z. And this should be equal to 0. So this will come out as free expansion along x is L alpha delta T minus effect of sigma x, which is sigma by E into L plus effect of sigma y and sigma z. So plus mu times of sigma by E into L. This is effect of sigma y. Then effect of sigma y is mu times of sigma by E into L. And this will be your complete equation. So this is your complete equation for calculating the total deformation, the delta net value. Okay. Now next is delta net along y should be 0. So this is equal to free expansion along y, free expansion along y minus effect of sigma y, minus effect of sigma y. Then you have the other two stresses which will going to increase the dimension along y. So plus effect of sigma x plus effect of sigma z, plus effect of sigma z, and this should be equal to 0. Okay. So using this you can write down. So free expansion along y is equal to h alpha delta t, then minus effect of sigma y. So sigma by E into h plus effect of sigma x. So plus mu times of sigma by E into h plus mu times of sigma by E into h, and this should be equal to 0, right? So this is your equation along y direction. Similarly, you can write down equation along z direction. So delta net along Z, delta net along Z is equal to 0. So this includes free expansion along Z, free expansion along Z minus effect of sigma Z, minus effect of sigma Z plus effect of sigma Y, plus effect of sigma Y plus effect of sigma X, plus effect of sigma X, and this should be equal to 0, right? So you can write down free expansion along Z is equal to B alpha delta T. Effect of sigma Z, this is equal to minus sigma by E into B. Then effect of sigma Y, so plus mu times of sigma Y, sorry, this is sigma by E into B plus mu times of sigma by E into B, and this should be equal to 0, right? So this is how you can write down all the delta net along X, Y and Z direction, and this will going to help you to analyze any question of the thermal stress, right? Any question of the thermal stress can be analyzed if it is restricted along one direction, two direction or three direction, okay? So this is the thing. So this I think completes the revision of the first chapter, which is simple stress and strain, which is again the longest chapter. Now coming to the second chapter, that is known as your shear force and the bending moment diagram. Shear force diagram and the bending moment diagram. Shear force diagram and bending moment diagram. I write here bending moment diagram. Okay. Shear force diagram and the bending moment diagram. Now, if I have to just summarize this to help you to recall this in just 1 minute, I will say I'll make a table like this. So here I have a loading. Here I have a loading, then shear force diagram and the bending moment diagram, okay. Now the thing is, if my loading is point load, and this point load is acting upwards, if my point load is acting upwards, then in the shear force diagram you need to move up. At the same location in the shear force diagram, you need to move up. Right? At the same location where this point load is acting upward, in the shear force diagram, you need to move up by the same amount. If the load is 3 kilonewton, then in the shear force diagram, you need to move up by the amount of 3 kilonewton. In the bending moment diagram, there will be an effect, but that effect will be the linear effect. That effect will be linear effect, linear upwards. It will be linear upwards. That effect will be linear effect, and that will be linear upwards. If your point load is acting downward, then in the then in the shear force diagram, you need to move down by the same amount. And in the bending moment diagram, again you need to increase 1 degree. This is linear downwards. You just remember this table. We will solve few things and you will very easily can relate with this, right? So this is whenever point load is there, in the shear force diagram, you will see the abrupt change in the ordinate. If the point load is up, you need to move up. If the point load is down, then you need to move down in the shear force diagram. Similarly, in the bending moment diagram, correspondingly, there will be linear upward movement and linear downward movement that we will also see. Okay. Now, if it is a UDL, right? And if your UDL is acting downward like this, then over this span where UDL is acting, In the shear force diagram, you need to move downwards. So you need to move linearly downwards. Linear downwards. You need to move linear downwards. You need to move linear downwards. Here you will going to have parabolic variation. Whether it is upwards or downwards, that is an issue that we will going to solve once we get the question. The thing is, whenever you have a UDL, and that is UDL is acting downward, then for the shear force diagram, it will move linearly downward over that portion. If you have a UDL which is acting upward like this, right? Then in the shear force diagram, it will be linear upward movement. Linear upward movement. And in the bending moment diagram, again it will be parabolic. Means for bending moment diagram, you need to increase 1 degree. If this is constant, this will be linear. If this is linear, then this will be parabolic. Okay. If you have a concentrated moment, then there will be no change in the shear force diagram. But in the bending moment diagram, at that section where concentrated moment is acting, whether that moment is acting in the sagging way or in the hogging way, you need to move up and down. If this concentrated moment is sagging, then you need to move up in the bending moment diagram. If this concentrated moment is hogging, then you need to move down in the bending moment diagram. So if the moment is sagging, then you need to move up. In the bending moment diagram. If your bending moment is hogging, then you need to move down in the bending moment diagram. Just remember these 3 things. If you remember these 3 things, your question solving will be very easy. Chalo, let's see some of the questions. First one is, if you have a beam like this, we will going to deal with this quickly, right? If you have a cantilever beam like this, and over this beam, you have a point load. Acting like this. P. You need to draw the shear force and the bending moment diagram. Right? Now for that, what you need to do is, first, wherever you have a point load, you need to move up. Okay. One thing I forgot. What is shear force? Shear force at any section is the sum of all the transverse load that are acting either to the left or to the right of the section. Similarly, what is bending moment? Bending moment at any section is the sum of the moment caused by all the transverse load either to the left or to the right of the section. If I talk about the sign convention of the shear force, okay, so if this is my section, on the left side of the section, upward load is positive, and on the right side of the section, downward load is positive. So this is your positive sign convention. Again, if this is your section, on the left side, downward load and here upward load, this is taken as negative. So this is the sign convention I will follow. Okay. Right now, if I talk about this beam, if I take any section XX, this section XX is on the right side, and right side downward is positive. On the right side, downward is positive. So if I need to draw the shear force diagram, I draw it like this. Downward is positive, so I'll move up like this. This is how I move up. From this point to this point, there is no load acting. So my shear force diagram will be constant. Then again, at this support, I need to move down by the same amount. So this is my shear force diagram, SFD, and this SFD is positive. Shear force diagram. For drawing the bending moment diagram, again, when you have a point load in bending moment, you have to move linearly downward. So you'll start from here, you move linearly downward like this. So this is your bending moment diagram for this cantilever beam, which is subjected to a point load. And this is negative. This is your bending moment diagram for this cantilever beam. This is your shear force diagram. This is your cantilever diagram. Bending moment diagram. Next, if you have this cantilever beam like this, which is subjected to UDL, if you have a cantilever beam like this, which is subjected to a UDL of intensity W kilonewton per meter, okay, and you want to draw the shear force and the bending moment diagram for this beam. So it goes like this: shear force diagram, bending moment diagram like this. So again, if I take any section XX on the right side, downward is positive. So I'll start from here and I'll move like this. This is downward positive, right? So this is your shear force diagram for this cantilever beam, SFD. For drawing the BMD, again, if it is a UDL, you need to move linearly. Sorry, the curve will be parabolic and it will be downwards like this. This is your shear force bending moment diagram for this cantilever beam. It will be parabolic like this. This is your parabolic curve like this. This is your parabolic curve like this, and this is your bending moment diagram. And this is negative, right? So just by observing this, you can draw the shear force and the bending moment diagram for all the cantilever beams. Now talking about the simply supported beams. So this is my simply supported beam subjected to a point load at the midspan. Subjected to a point load at the midspan. Subjected to a point load at the midspan. So this is my load P at the midspan. This is L by 2 and this is also L by 2, right? Now what you can do is, first of all, you can calculate the support reactions. So due to this point load at midspan, here the support reaction is P by 2 and here also the support reaction is P by 2. And this support reaction is acting vertically upwards. So for drawing the shear force diagram, you can go like this. For drawing the shear force and the bending moment diagram, you can go like this. So this is the shear force diagram, right? This is the shear force diagram. So at this point, you have an upward acting load of P by 2. So I need to move up by the amount of P by 2. Then up till this point C, up till this point where this point load is acting, there is no load. So shear force is constant. Then at this point, I need to move down by the amount of P like this, okay? Then between these 2 points, there is no load. So shear force diagram will be constant like this. So this is my shear force diagram and this closes here. So this is positive here, this is negative here, this is P by 2, this is also P by 2. Then this displacement is P, this displacement is P. So this value will be minus P by 2 and this is my shear force diagram. This is my shear force diagram, right? For drawing the bending moment diagram for this beam, again, for drawing the bending moment diagram for this beam, I will go like this. For drawing the bending moment diagram for this beam, so this is my bending moment diagram. So whenever you have a UDL, so point load which is acting upward, so in the bending moment diagram you need to move linearly up. In the bending moment diagram you need to move linearly up like this. in the bending moment diagram, you need to move linearly up like this, right? Then due to this point load, you need to move linearly down. So this is how you need to move down like this. So this is your bending moment diagram, and this is all positive. This is equal to PL by 4, and this is your bending moment diagram for this beam. Okay, so means shear force diagram and bending moment diagram are more general things. Okay, so you can practice more on that. Try to apply this concept. So easily we have revised 2 chapters of strength of material. So I think enough content for today. We got a lot of things to remember. First chapter is the longest chapter where we can expect a lot of questions. Okay, so from first chapter you can revise all the things. Again, if you feel like, you can watch the videos. If you have any doubt, again you can join our Telegram group, contact the mentors and post your doubt there itself. No problem. So this is the thing. Moving on with this. Chalo, I have last few announcements for today. First of all, my dear students, the link of the Telegram group is given in the description box. Join our Telegram group to get the lecture PDF, lecture schedules, to enjoy the daily quizzes. And we at IMS Gate Academy, again I would like to tell you, offer 4 different types of program where we provide you with 800 hours, 850 hours of live teaching, along with test series, live interaction, my plan sessions, theory and exercise book is provided to you. Along with that, we provide you with a GATE question bank in which 30 plus years of questions are there. Okay. So this is all the announcement. This is all for today. I hope you have learned a lot of new things. You have revised a lot of content. I'll see you tomorrow on the same IMS Gate Academy YouTube platform. You can check our playlist for watching all the previous sessions of Smart Revision, especially for civil and mechanical engineering students. We have also conducted GATE Score Booster series where you can enjoy the flavor of good questions which are framed from this subject of strength of material. So this is all for today. Myself Prateek Mishra signing off with a smile, and I wish you all the best, and I wish you to see you again tomorrow on the same IMS Gate Academy YouTube platform. Thank you so much. Have a great night ahead.